All right, so let's call this bug.c. And I'm just going to copy the usual. We might not need stdlib, but just in case. And I'm not going to need arguments. And I'm going to want to print all the characters up to the last one, right? So I'm going to say for char c equals. Let's avoid the non-printable one. So we're going to start at space. If you remember, this is the character with the lowest code. All right. C less than 1 to 8. C plus plus, and we're going to have printf percent C. Okay, so this prints exactly one character. What do you think this program will do? Seems quite innocuous and yeah, so that's what you think. Print everything from space to the last one. The last printable character has code 1 to 7, right? And then stop. Okay? So let's see if that happens. Bug.c. Haha, I'm caught, but let's let's overlook that. So see, at least the compiler has evolved, right? It catches this kind of things, right? 10 years ago, or 20 years ago, it didn't. So we're in an infinite loop, and the character with code 7, right? We're printing from 32.1 to 8, but somehow we managed to print the character with the code 7, which is the audible bell, which is why you're hearing that sound, right? So if I print 7 here, I'm going to hear bells, right? I'm going to hear there's just, oops, right? So the character with code 7, not all terminals, you see this is a terminal, this window is a terminal, not all terminals honor that. I think I can also go somewhere in the configuration and make it silent if I want to. I'm not going to bother to do that, right? But we're printing C. So what's the problem here? Why are we going into infinite loop? Yes?
I will always be less than 1. It's counting from 0.
Exactly, right? So what's the range for C? C has 8 bits, right? Remember, it's a character. Has 8 bits. And I didn't say unsigned. I said I let it be signed. So what's the range for C? Well, don't count in your head. Tell me as a formula. What's the lowest number? For char, right? Minus 1 to 7, right? So it's minus 2 to the power of 7, right? So we have 8 bits, right? So whenever we have n bits, if that is considered a signed number in the complement of 2 encoding, right? We go minus 2 to the power of n minus 1. The exponent is n minus 1, right? What's the highest range? 2 to the power of 7 minus 1, right? 1 to 7. So you see, what's going to happen as I increment C++? I'm going to reach the value 1 to 7, and 1 to 7 plus 1 is going to be minus 1 to 8, right? We have 8-bit numbers. So this is always true. Therefore, we have an infinite loop. Very common source of bugs. Okay? The number 1 to 8, represented here as a constant, okay, is an integer, is an int. Right? Whenever we perform this comparison, it's a signed int. Always it's a signed int. That's what the definition says. If I want to make it unsigned, if I remember correctly, I would have to say here u. Not that it matters, right? But one solution here would be to say, instead of char, right, I could do unsigned char, right? So if I do that, then the range changes into what? Into? Yes. So it goes from 0 to 2 to the power of 8 minus 1, right? Which is 255. Which, if I keep incrementing C, we're gonna, how is it gonna go, right? So from whatever value, we're gonna keep incrementing until we'll hit 255. Then 255 plus 1 is 0. Very good, right? So this test here has clearly a chance of becoming false, right? And therefore we will exit the loop. So let's try that. Okay, and you see that we have all the characters from space. This one is, we have a space here, right? Up to the last one, which is tilde, and then it stops. Okay? So that's a solution. All right? Whenever, so I started saying that whenever you see digits like this, right, they are considered signed integers. If you want to have unsigned integers, you will have to say this. If you want to have this number as a long, you can add an L. All right. I'm not quite sure how you make it into a short, and I haven't had a need to work with shorts for a very long time. But it's often needed to work with characters, right? So if you want to make it a character, you will have to use hex, unfortunately. So either you can say this is tilde, right? But this is actually 1 to 7, right? So we could actually just say that, and then the code will go up to here, right? Or we're going to learn quickly, very soon, right? I can say something like backslash x 80, and this is going to be 1 to 8, and I'm going to explain in a minute what it is, right? The important thing is that in general we can create constants of the appropriate length whenever we need them. All right. So if I want a character 8 bits, right, I can create it with whatever value in this way. I'm going to explain this notation very quickly. Another way of doing that is to use a type conversion, which in C is called a cast. So one thing we could do is say char 1 to 8, right? So char 1 to 8 actually is going to be minus 1 to 7. Minus 1 to 8. Right? Okay, let's do that. Not clear why? And if we want it as an unsigned, char, we can say this, right? Whenever we put a type in brackets in front of an expression, that expression is converted to that type. And generally by type we mean length, right? So what's going to happen is that if the original value has more bits than the desired result, some bits will be stripped off, right? So only some of the bits will be preserved. If you have more bits than the original value, then it will be extended, right? How? We discussed last time, right? If it's unsigned, we will pad zeros. If it's signed, we will pad the signed bit so that the sign of the value is preserved. All right, so none of these things will actually change the result in this case. The interesting thing is what happens when we have operations between two different types. So here we have a comparison between a character and a integer, right? They have to be converted to the same type. How are they converted in a case like this? They're converted in a manner that no bits are lost. Bits may be added, but no bits are lost, right? So if we want, if we want to do that, we have to extend C to an int. All right? But notice the fact that the extension happens only for the duration of evaluating this expression. It's a temporary value, right? So I keep C as it is, but I copy the value into something temporary. I convert that temporary thing into an int. Then I perform this comparison. And then when I do C++ here, I will still perform an operation on the original 8 bits, right? So when I'm going to reach 1 to 7, C++ is going to give me minus 1 to 8. Okay? Very quickly, let's just print f percent d \n, and I'm going to print, what was I saying I would print? Char of 1 to 8. Right, and I was saying that this actually will print minus 1 to 7, right? Pardon? Or minus 1 to 8. There's a semicolon missing here. Right? It's clear why, right? Because I'm taking the last 8 bits. And then, so this number as a, let's assume it's a short, because I don't want to type too many bits, right? So I only have 16 of them, right? So this as a as a short number with 16 bits, it's going to be 8 zeros. I think there's 8 there, a 1, and then 7 more zeros, right? That's what it is. So that's the value 1 to 8, right? If it's an int, I'm going to have to put in front here. I'm going to have to put 16 more bits. If it's a long, in front of the 16 more bits, I have to put another 32 more bits, right? But let's assume it's that, right? What happens when I convert this to char? We'll actually strip off 8 bits. Because we only can keep 8, and we'll always keep the least significant ones, right? And now, this is a signed value. Obviously, whenever a signed value has the first bit equal to 1, it's negative, right? So it's minus 1 to 8. So this is the major source of bugs in C, right? You have to keep that in mind and pay attention to it. And essentially, if you want to not care so much about it, you will still have to care every once in a while, right? Go into a language that doesn't deal with so many types of integers, right? So Java has only one type. It's only int. There's no unsigned. There's no signed. Well, actually, it has two. It also has long. So nowadays, right? Because there's the 32-bit integer and there's the 64-bit integer. Python only has numbers, right? It will automatically switch between them and always take care of that, and has infinite precision, so you never have to worry about that. JavaScript is very tricky. Yes? Yes, it's different from int, and we're going to discuss that. And actually, conversions from between int and double are sometimes tricky in Java as well. Yeah, I mean they're as tricky as just they have fewer int types to worry about. In JavaScript, it's tricky because you don't have int at all. You only have doubles, right? But the doubles are disguised as ints, and that comes and bites you in the back every once in a while. Cool. So what I want to talk about next is hexadecimal notation. Have you encountered it before? How many of you have? Okay, cool. So let me go through it very quickly then. So far, you've seen me printing a lot of bits, right? So I go and look at this kind of numbers and try to play with them and explain. And actually, looking at the bits is always very important, right? Just that it's too many numbers are too long, right? So what people have started to do a long time ago is actually group them 4 by 4, right? And invent a new system of digits, a new base for arithmetic, right? Which is called, it's base 16, right? It's called hexadecimal. How do you obtain base 16? We take the digits from 0 to 9, and we add the letters from A to F, which we consider digits, and we have 16 symbols to express numbers, right? The letters from A to F represent the so-called digits, the hexadecimal digits that have the values of 10 through 15, right? Now, because 16 is 2 to the power of 4, converting between binary and hexadecimal is very straightforward. We group the bits 4 by 4, and each group of 4 represents one hexadecimal digit. For instance, the first one is 5, right? The first 4 are 5, and then maybe I shouldn't make them so regular. The next group is 13, which is the letter D, right? And you can use either capital D or small d, it doesn't matter. I think the next one is also 5. Let's make it 7. So the next group would be here. So we can have 7, and so on and so forth, right? So the numbers are a lot shorter, and then a lot of people learn how to do hexadecimal arithmetic in their head, right? After a few years of doing this, it becomes very natural. So it becomes another idiom of a computer scientist. I'm going to show you this because I want to, first of all, explain those strange characters that we've been looking at. 2, I want to show you conversions between doubles and integers. I want to look again at different codes, and it's going to be easier to do it if I have hexadecimal numbers, right? So I was talking about characters, right? And you saw me saying \x 80. So 80, you have to look at them here as hexadecimal numbers, right? And if you look at them as that, 8 is 1000, 0 is 0000, right? So this is the number 128 in hexadecimal. We tell the system that this is a hexadecimal number by putting \x in front. Okay? And for instance, if I'm going to say here \x 41, and I don't want to put it here. Let's leave this as a space. And I'm going to do this here. So \x41, this should be the letter A. And I'm going to put it twice. I'm going to print it twice. Actually, I'm going to print it 3 times. Right, so first time I want to print it as a character, so you see the letter A. The second time I want to print it as a decimal number, and you should see the number 65 there if I'm not mistaken. And the third time I'm going to print it as a hexadecimal number. I'm hoping this is what, I'm hoping I'm remembering correctly. Okay, so so you see that we have A, which is the character encoding of the number of the code 641, right? We have the number 65, which is the decimal value of 41. And finally, we have the hexadecimal notation, which is actually 41. It's the same thing that you see here, right? We always have the option of printing something in hexadecimal notation if we so want, right? The specifier is %x. Now, just to convince you that this is just a value, I can put 65 here. We already know that 65 is the same as \x41, and we should see the same output, right? And this works. Okay, so perhaps for the purpose of this exercise, we can do away with that loop, and we see this out. Questions here? Cool? Okay. So the next thing that we're going to do is look at floats. Before we go there, right? So you've seen this \n a lot of times, right? And I told you that this represents a control character, right? It's the character that sends us to the next line. This backslash is a means of introducing all sorts of non-printable stuff, or stuff that doesn't print, that prints you something that you don't really see. All right? And we have a way of printing any character code as we want, exactly in the same fashion, right? So we're not restricted to using \x inside character constants, but we can use it here as well, right? So for instance, if I want to say the character B, right, I can say 42 here, right, and I will see a B at the end of my line. And yeah, let's keep this commented out. Everybody knows what a comment is? Yeah, you've seen it before. I mean, normally you use comments to explain the program, but one very neat feature is that you can comment out parts of your program that you don't want executed temporarily, so that you can test or debug. And this is what I'm doing here. All right, right. So then there I have a B. And if you want, you can try and experiment with all the characters, all the character codes. There's usually not a lot of benefit in this notation, unless it's a character that you can't produce from the keyboard, which happens with some Unicode characters, or you have some programmatic way of generating this string, right? That's another thing that you can do. Sorry, this string, right? So this string is a constant right now, but you might be able to produce it from something else and generate it, at which point this \x might become useful. And the question becomes, how do we print a backslash if we so want? Right, let's say I want to print a backslash right here. Well, you just double it, right? So the first backslash, usually it says that the next character is going to mean something else. But in this case, the second character just says that the backslash is indeed a backslash. So we can have that, oops, 2. All right, so you can see the backslash here. Cool. All right, let's try to leave the program a little bit neater. Okay. Floats. So, obviously the world is not made just of integers, right? We need real numbers as well, right? And how can we encode real numbers? That's one question, and there were many answers throughout the history of computing to this question, and then you might find the name float and double. You might find them strange, right? So that's because they represent. So float represents the concept of floating precision, right? Floating point arithmetic, right? It's a concept derived from scientific notation, where you might know this or not. Engineers frequently write down real numbers as a string of digits that is always normalized. So it has one digit before the decimal point, right? So one digit, then the decimal point, then a number of fractional digits, right? Times 10 to some power, right? And we can always express a number in that way. And that power can be either positive or negative. So for instance, the number 123.456 can be represented as 1.23456 times 10 to the power of 2, right? So in computing, actually, we go a step further, right? We want no digits in front of decimal point, and typically we don't write anything before the decimal point. And we denote the exponent by e, and here the exponent will have to be 3, right? If I have something like 0.00123 equals, this will be 0.123 e minus 3, right? So we always denote our numbers in this way, okay? This tells us a much more useful story, right? It tells us what's the error. The error, we're never interested, I mean, we're very seldom interested in the absolute error, right? I don't care that the error is 10 to the minus 14, right? I care if the number is in the trillions, right? Obviously, that's going to be a very good result, an error of 10 to the minus 14. But if I'm trying to measure the Avogadro's number, for instance, right? Or if I'm trying to measure, sorry, the atomic mass of some element, 10 to the minus 14 is huge, right? It's a very bad result. So the important the way to look at the error is actually to look at the relative error. How much is the error compared to the magnitude of what I'm trying to measure, right? And in that case, I always want to look at how many significant digits do I keep from a number, right? So the number of significant digits are digits that are not 0 either before or after the number, right? The preceding zeros and the succeeding zeros, I'm never interested in them, right? They don't amount to anything. They're not important, right? I can always put them as an exponent. Everything that is non-zero at the extremities, right? So zeros at the extremities don't count. So this 0 doesn't count, right? All these zeros don't count. And if I have something like 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, these zeros don't count, right? So this is equal to, I don't want to count them. Let's have 3, right? So I'm going to have 0.123 E6, right? So that's good enough for me. I don't have to know more. Yes? Do I not do what? Again? I don't understand. This is decimal digit, yes. So you can assume that there's a 0 in front of it, but I don't care to write that 0. I was telling you that that's how the engineers typically do it, but the computer doesn't do it that way, right? The computer will not have right? We'll always have 0 before the decimal point, right? So this is what we call a mantissa. This is what we call a mantissa, right? Okay. And this is what we call an exponent. Okay, understood? It's no big deal. It's just a matter of convention, right? You minus 2, that's true. Okay. Okay, so I understand now. This was the misunderstanding. Okay, understood. Okay, good point. All right, now, what we did before was to look, numbers were written in base 2, right, as bits. So real numbers should also be written as bits, right? We should have a base 2. Now, the same principle applies as compared to the base 10. So if I write the number 0.123, right, this is equal to what? 1 times 10 to the power of minus 1, right, plus 2 times 10 to the power of minus 2, right, plus 3 times 10 to the power of minus 3. So if I'm going to write something like 0.1101, this will be in base 2. This should be equal to what? Right, so it should be 1 times 2 to the power of minus 1. So I'm just going to say 1 divided by 2 plus 1 divided by 4 plus 0 divided by 8, right? Plus 1 divided by 16. Does it make sense? How do we convert from a number in base 10 to numbers in base 2? Real numbers, fractionary numbers. So I'm going to take, let's say, something that is not overly complicated, 0.8. All right, so this is base 10. How do I find the decimal notation? No, let me take one that is really easy, 25. All right, 0.25. So how do I find the base 2 equivalent? So what would I do normally if I were converting 25 into base 2? I would divide by 2, right, and take the remainder, and I would divide by 2 again, take the remainder, right, and keep going until I'm left with 0, and I will take all those digits and write them in reverse order, right? So the last that I computed will be the first to write, right, and go backwards until the first that I computed, which becomes the last to write. Now here, because we have fractionary numbers and we're on the other side of decimal point, we're going to multiply by 2, right? So we're going to say times 2. So this is equal to 0.5. So I'm going to take this 0 as the last computed digit, right? And this is below 1, so I'm going to keep it the way it is. So then I'm going to do 0.5 times 2, and I'm going to get 1. And this is equal to 1. Whenever I see equal to 1, I subtract 1. Right? And then I'm left with 0, and I can be done. Right? So what I see here is 0, 1, right? So and because it's fractionary, we're not going in reverse. We're going direct. So the final value is going to be 0.01. So I have this 0 is this 0, and this one here is the last one. Okay? And this is a very easy case. This is how I convert. Okay, and this is indeed true because I have 0 divided by 2 plus 1 divided by 4, that's 0.25, right? Now, a very interesting case will happen. I'm going to try to convert 0.8. Okay, so times 2 equals 1.6. So see, here I have 1. I'm going to subtract this 1. I'm going to remember it, but subtract it. So here I'm going to be left with 0.6 times 2. I'm going to have 1.2 now, right? I have another one, which I'm going to subtract. So I'm going to be left with 0.2 times 2. I'm going to have 0.4. So I'm going to remember this 0, right? And then 0.4 times 2 is equal to 0.8. And we're in trouble, right? Why we're in trouble? Louder? It'll loop, right? We started with 0.8, we got back to 0.8, we're going to go like this forever. So what's the representation of 0.8? So again, we start with this one, right? 1, 1, 0, 0, 0, right? So 0.1100, and then 1100, 1100. Okay, obviously I can't go forever. I have to stop at some point. Okay, but there's a very important lesson here. There are numbers which in base 10 cannot represented, which are finite in base 10, cannot be represented finitely in base 2. We're going to have a conversion error no matter what. All right? And this conversion error can add up. Is that clear? Okay. Now, how are floating point numbers represented in the computer's memory, right? So we're going to take either 32 bits or 64 bits, right? Because that's the unit. That's sort of that's what the computer tends to handle very well. Right, a multiple of 2, but nowadays it's either 32 or 64. Actually, you can go up to 128. And it will divide these bits in a way that we can represent the mantissa and the exponent and the sign. We haven't said anything about the sign, right? So out of 64, 1 bit is going to be the sign. Right? If we use 64 numbers, 64 bits, right? About 53 digits are going to be the mantissa. All right? And about 10 bits are going to be the exponent. The exponent is represented in complement of 2. All right? And what happens for a float when we use only 32 bits? So let's write this down so that you have a good image. So we can use 64 bits, which everybody is doing this day, and we call that a double. And it stands for double precision. Double precision floating point real number. That was what initially was called. We are left with double in 2018, but actually we've been left with double since the 80s, I think, right? So this is a double, and it has 53 bits of mantissa and 10 bits of exponent and 1 bit for sign. The alternative is 32 bits, which I haven't seen used in a long time, and that's called a float, right? And it was called floating precision real number. Later it became floating point real number. Then it became single precision floating point real number, right? But it is generally known as float. Not in very widespread use. Uses fewer than, obviously, so out of the 32 bits, I can't remember very well how many there are. I think it's about 7 bits of exponent, and it's about 23 maybe of mantissa, and 1 bit of sign. We can't get rid of the bit of sign, right? So this can represent numbers in decimal between 10 to the power of minus 300, around there, right, up to 10 to the power 300, right? So that's the range that it represents. but it only has about 16 digits of precision, decimal digits of precision, right? It doesn't matter that it has 300 zeros. You will only know only the first 16 to 17 digits, right? Because we're always interested in relative precision. We're not interested in absolute precision, right? And similarly, if you're trying to to store a very small number, right? It might have 300 zeros after the decimal point, but you will only know about 16 digits after that, right? So you can have a number that is 0.00. You have 300 zeros, but now here your number might be very long, but you're going to know only about 16 digits out of them. I don't know exactly how many of them is 16, but you're going to know a limited number, right? That's the mantissa. That's the result of 53 bits of mantissa, right? It converts into about 16 to 17 decimal places. Clear? So now what's going to happen if I add a very large number with a very small number? It will have no effect, right? So if the exponent between the two numbers is more than 16, 17, right? Then the smaller number will have no effect on the bigger number, right? So that always you have to keep in mind, right? So you might say, oh, I'm going to add 1 million. I'm going to add a small number 1 million times. Each time you add it, makes no difference, right? You haven't changed the bigger number. Whereas, if you take the small number, you multiply it by 1 million, and then you add the result, right? Then you get a number that might be significant enough to make a difference, right? So in this case, the order of the operations essentially matters, right? Now, let's see. Let's try to see that. Let's try to experiment with that. Okay, let's leave this as it is and create a new program which we call floats. Okay, let's include this thing. So we're going to use doubles. And let's start with A, whose value, we're going to make it 1, 2, 3, 4, 5, 6, 7, 8, 9, E 20. All right, so double B equals 9, 8, 7, 6, 5, 4, 3, 2, 1, E minus 20. Okay, and then we're going to printf result, and if I remember correctly, this is LF backslash n. We're going to print A plus B. All right, so okay, let's do the following, because there's more to see this. Let's say we say A equals, and then %LF backslash n, then B equals %LF backslash n, and then we print the result. So let's print A, B, and A plus B. Okay. So first of all, b is 0, right? Why is b 0? I know why b is 0. So b is printed as 0. So C printf double scientific notation. So let's try percent dot 10 e. So that should give us the scientific notation, and we should be able to see. And actually, I don't want 10. Let's put 17. We're supposed to have 17 digits. So let's get as much as we can. Actually, why not 20? Let's get more than. That's going to be interesting. All right, so we can see that this is not 0. All right. But one thing that we're seeing here is that we don't get back exactly the same value that we have put in. Right? Why is that? Well, this number was converted into base 2 and then converted back into base 10, and in this process lost some precision. Right? And also we're seeing that the value of the result is exactly the same as the value of A, right? Which is because B was too small to make a difference, right? Another interesting thing that we can say here, we can check here, is whether it's equal. So we can say is equal, right? So we're going to have 1.1 for true, 0 for false, right? So let's check whether A is equal with A plus B, right? And we're going to see that happening, right? They're equal. Now, obviously, if I'm going to change this value to something more, so let's change both these values, right? So let's make this 5, and let's make this -5, right? So now you can see that they're different. So A and A plus B are different, and is equal is 0, right? So when the numbers are closer in value, right? So the difference, it's not the difference, right? The order of magnitude, the difference in order of magnitude is more than 16, then it won't make a difference. If it's less, it will. Okay? Let's do another interesting experiment. I'm going to start from 0 and keep adding 0.1 to 0 100 times. 0.01. 100 times. And I would expect to get to 1, right? And I equals 0, I less than 100, I plus plus, and here let's do some plus equals 0.01. And then let's declare double sum equals 0.0. Or actually I can say just 0.0. And print sum. Percent. Here we can say LF. So F is float, and LF is long float, all right, which means double. Again, these are sort of consecrated notations. Nobody thought of changing them. They're not terribly consistent. They made sense to somebody at the time when they were created. Oh, and we're getting 1.000. Okay, so we haven't exposed the error because but the error is there. Just that printf is smart enough when it performs this conversion to actually think that it's close enough to 1 and let's make it 1. So I'm going to use here again 0.20e and see all the decimal places. Right? So you see that there's some residue here. Right? It's not exactly 1. So if you're printing only the first few 5 decimal places, right, then you're seeing 1, but actually it's not. We can expose it even further if we add more zeros, right? So let's do it 10,000 times. So the error is going to be worse and worse, right? So now it's 0.99999, right? If I go even further, it's going to go even more. And I think at this point, I can actually just say LF here, and we're going to still notice the error. No, smart enough to figure that one out. But let's go to 1 million. Because we should be able to handle 1 trillion without much. Still smart enough to. So again, in older times, you would have seen this earlier with fewer iterations because the library was not as good. But these are things that have improved, right? Because the need for precise and fast arithmetic calculations has increased over time, right? So people have put efforts into doing arithmetic in a faster and more precise manner. Remember this, okay? It's one of the important things you should know about floats and errors, right? Java has a new type nowadays, which is called big decimal, all right, which is trying to work with as precisely as possible with numbers in base 10. So they don't even convert in binary. They keep numbers in a base 10 encoding so that they wouldn't get this conversion errors, right? And I'm going to use Scala, which is a language that is built on the JVM and takes advantage of this libraries and where big decimal is very nicely exposed, right? And I am going to okay, let me define a number A, which is new. Actually, I don't think I need new big decimal of. I can create this number from either doubles or strings. So I can do this. It's smart enough. And I can do val B equals big decimal, and I will use this string. Do you think A is going to be equal to B now? Oh, that's unexpected. I would expect it to not be equal to. I haven't used Scala in quite some time, so maybe certain things have changed, and also Java in quite some time. Seriously? Okay. So what would happen normally, right? And that's a question I used to ask in interviews, where in banks where this is a very widely used library, right? So you take the 0.2, right, and you convert it in base 2. So just from this notation, because this is a double, right? Just from this notation to its binary, we have lost some precision. And then you're creating this number that is supposed to not have any loss of precision for decimal, but you have already lost some. Because the system reads this as a double. Whereas if you put in a string, that loss of precision doesn't happen. It's a string. Then you can go and analyze the characters, so this big decimal can create a number without any loss, right? So what used to happen in those days, that was not very long ago, a couple of years back, was that this was false. And then the question would come, what value would I put here so that this works? This equality works. Is there a value for which it would work? So can you tell me what are the values for which there's no loss of precision? Because we've seen that, for instance, for 0.8, there's a loss of precision, right? And then when we were looking at 0.8, right, in the process of computing the decimal representation, we've seen 0.2, 0.6, 0.4. So because they were there, if we had that as a starting point, we would cycle on those as well, right? So it is to be assumed that it wouldn't. So what kind of values do you think would not cause a loss of precision? Yeah. Yes, good, very good. So 0.5, so no loss of precision. 0.5. What else? Louder? 0.25. 0.75. Okay, you got the idea. So what's the rule? Yes, right? So anything that you would write as a finite sum of fractions, so k1 divided by 2 plus k2 divided by 4 plus k3 divided by 8, and this is a finite number, right? So you pick whatever finite number of powers you want, and you pick k1, k2, k3 to be whatever you want, right? So they can only be 0 or 1, obviously, right? And then that's going to be something that gives you finite representation, right? So so what you can create by varying k1, k2, k3 is these numbers: 0.5, 0.25, 0.75, 0.125, 0.325, I think, right? For 0.375, sorry, 0.625, right? All these numbers that are expressed like this, and essentially, if you would write them in without the decimal point, they would be multiples of powers of 5, right? That's what they would be. So all those numbers would not cause any loss of precision. Okay, anything else will. Anything else will. All right, so keep that in mind also. All right, and the final point of this evening, we're going to introduce a new construct, which is called union, and which makes this aspect of the same bits multiple representations a lot more apparent. So that's what we're going to try to do now. So in C, we can define new types, right? And we're going to. There are several ways of doing that. All right. One new kind of type is the union. You may or may not want you to name it, so I'm going to put it in the general form. So I'm going to say type def here, type def union, and I'm going to give it a name. And I'm going to call it hodgepodge, because that's what we're going to try to make. So what's a union? A union is a way of looking at the same area of memory at the same bits in different ways. All right. So I'm going to have 8 bytes, 64 bits, which is 8 bytes, right? I can't access the bits in entities smaller than 8. The smallest is 8, and it's a character, right? So 8 bits is 2 hexadecimal digits, right? 1 byte is 2 hexadecimal digits, right? So I'm going to have something like 00, 00, 00, 00, 00, 00, 00, 00, 00, right? So these are 64 bits represented. 64 bits of zeros represented as hexadecimal numbers, right? And I could have something like FF, 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 right? So it's a way of filling 8 bytes. Okay. So how can I look at these 8 bytes? First of all, I can look at them as a array of 8 characters. Each 8-bit entity, each byte entity represents 1 character. So I can say here chars 8. We look at it as 8 characters. Another way of looking at it would be as 4 shorts. Shorts 4. Okay, each short is 16 bytes, 16 bits, 2 bytes, and we could fit 4 of them. We could look at it as 2 ints, right? And int 4. We could look at it as 2. We could look at it as 1 long int, right? So we can say longs 1 long. All right, give it a name. We could look at it as 1 double, right? The same bits, every time I'm going to select one of these selectors, I'm going to see a different encoding of those same bits. Okay, and we want to see what we get. All right, so 1 double. What else can we see? Well, we can see them as unsigned ints. Same length. All right, we can see them as long. Okay. We could see them as unsigned chars. I'm not sure if it's worth doing that. Maybe it is. All right. So I have this type, which is our own. So I can use it to declare a variable a. And guess what? I'm going to say a dot 1 double equals 1, 2, 3, 4, 5 point 6, 7, 8, 9. All right. So let's start printing. And I'm going to say as chars, and I'm going to say percent %x, %x, 8 times. I have 6% x, and backslash n. Okay, and here we're going to say a.chars 0, and normally we should write a loop, but I'm going to sort of try to use a pattern here, so I'm not going to bother. This is just for the purpose of learning. We want to be quick. 2, 3, 4, 5, 6, 7. Okay, so let's see what we get. So we're printing all the 8 characters that we have in that space. You see, we filled that space with this double value. The bits have taken some values depending on the double encoding, right? And no. Okay, cool. Okay, so all right, I'm going to print the unsigned characters. Sorry, I should have printed the unsigned ones. Because they some of them get to be negative. Stop. All right, so these are the bytes that correspond to the double number, right? Now, let's see, what is this encoding actually? And we're getting very quickly to that page. This is the standard, all right? And so we have sign bit 1, 11 bits of exponent, 53 bits of mantissa, of which 52 are explicitly stored. Why? Because the first one is always 1, so we don't have to store it, right? So this is how it looks like. Okay, and let's try to do the following. Let's try to increment the exponent. Let's try to multiply it by 10. All right, but not by multiplying by 10, but by selecting these bits, 11 of them, and incrementing that number and putting it back. All right. So so the question is, let's see if we can try to understand the value that we're having, right? And in order to do that, let's actually take a simpler number. right? So instead of taking 1, 2, 3, 4, 5, let's actually take 0.5. Okay, and see what kind of encoding do we have for that, because we know that that works very well. All right, and this is where we're seeing that the 64th bit is actually in here. Right? Oh, it's complicated because there's a biased exponent. All right, so the number 1, this is how it is represented, right? All right, let's start with the number 1, and this would be an interesting thing to solve. So we want 1.0 here. So we have F03F. So one thing to understand now is that this number is essentially reversed. We're seeing the reversed bits. All right, and we're going to talk about NDNS shortly. So we have F03F. Okay, I'm gonna do the following interesting thing, and let's see what effect it has, because it's running short. I am going to increment. I'm going to do a dot chars of 7 plus plus, and let's print the double, right, as double %LF \n, and let's see what value do we get. Can you explain that value? A dot 1 double. Right? So we started with the value of 1. We incremented, right? This value of 1 is a double number, right? It is laid out into 64 bits in memory in a specific encoding. Where do we go then? We take the last byte, looking at it in isolation, and we increment it, right? And then we see what the effect is. And we get a completely different value, right? So it would be interesting to try to understand exactly how this value is obtained by looking at the Wikipedia page, but I don't think we have time. So I'm going to leave that as an exercise. What I want you to draw from here is that we're essentially now looking at the same bits through two different encodings. We applied two operations, each of them through the prism of its own encoding, right? And we got two different values, right? Which is something that is expected, because for this operation, what you have is garbage in, garbage out. Okay? But this is another thing that causes a lot of bugs, right? Now, I want one more thing, right? So I want to create another another value and give it some meaningful, fill the bytes with some meaningful values, right? And I'm going to actually fill it B, and I'm going to say B dot unsigned long, and I'm going to put the following value in there. So I'm going to put a hex value, 0x. If we are in as a constant, we, instead of using quotes, we can put a 0 in front, right? 0x, and I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, and I think that's enough, right? 8 of them. Okay, and let's now do the same thing. Print the characters. Okay, so now we're going to see something that we understand. It's a lot easier to understand. Maybe I should have started with this one, right? And we're saying as chars. So and obviously I want to print B. Maybe I should have overwritten A. Okay, so notice how they appear in reverse. Actually, it's not enough of them, but nevertheless. So notice that 1, 2 is here. Then we have 3, 4. Then we have 5, 6. Then we have 7, 8. Okay, so nevertheless, every byte is recognizable. All right, so let's keep going then. 8, 9, A, B, C, D, E, F. And let's do it again. Right, so notice how they appear in reverse order. Okay, what do you think is happening? Okay, let's do another one. Let's print as shorts. And I'm going to, no, let's not waste time. Let's print as unsigned ints, as U ints. And we're going to have only 2 of them. And then we're going to have one unsigned, right? Okay, so again, notice how they're, I mean, inside the number, they appear in the right order, but they're reversed. Okay, what do you think it's happening? All right, so I have this number, right? So what's the most significant digit? The 1, right? So I would do 1 times 16 to the power of 16 plus 2 times 16 to the power of 15 plus, right? That's how I would produce this number, right? Now, if you look carefully here, where's the 1 sitting? There's a 0, 1 here, which we're not showing. It's sitting at the end, right? So they're essentially stored in reverse order. This is called a little endian architecture, right? So have you heard of endianness? So when I lay out the digits of a number in memory, right? You can think of the memory as being a string of bits, an array of bits, right? It goes from bit 0 to bit 2 to the power whatever, right? And somewhere in the middle, somewhere there, I'm going to reserve 64 of them to put my number, right? And then, how should I put my number? What digits should go first at the smallest index? The thing is, there's no rule. I could put the most significant bit of my number there, or I could put the least significant bit of my number there, right? So guess what? Historically, both of them are in widespread use, right? Intel chose to go with the least significant bit first, whereas Motorola, which was back in the day was a prominent microprocessor producer, chose to put the most significant bit first, right? The Motorola convention was taken by Sun Microsystems, which produced the SPARC processor, and then so that was around the Stanford the Stanford nucleus of people who developed the RISC architectures, which produced a wide range of processors, which ultimately led to the ARM processor, which now everybody has in their phone, right? So those processors actually use the big endian, right? The most significant bit goes at the lowest rank in memory, whereas the Intel has the least significant bit goes at the lowest rank in memory. So we're in a small endian. Intel is called small endian, and the other one is called big endian, right? And the name endian, where do you think it comes from? Who knows? Why it's small endian, big endian? Comes from Gulliver's Travels, right? Have you read Jonathan Swift's book, Gulliver's Travels? So Gulliver is this traveler who goes first into a place of giants and then into a place of midgets, right? Of small people, and so that's his travels. And it's a satire directed at the political world of Britain of his time, right? And then when he was in one of these worlds, right, because it was a satire, there was a big debate of whether an egg should be cracked at the small end or at the big end. All right, so that's where it comes, small endianness and big endianness, right? Because as that debate was completely useless and had no point, the debate of whether computer architectures should have a big endian kind of encoding or a small endian kind of encoding was equally pointless, right? So both architectures survived and thrived, but back in the day there was a big debate, and various people would argue in various ways that it should be this or that, right? Notice again, right? That's what I'm. This is the last time I'm doing it, right? Same bits, different encodings, right? We're looking at. So all these are different layouts for the same set of bits, right? The same 64 bits. I can look at them as 8 characters, as 4 shorts, 2 ints, 1 long, or 1 double, right? And every time I use that particular selector from the union, I'm going to see something different on the screen, right? There's a different underlying encoding assumed about those bits. All right? So it's very much in the eye of the beholder, so to speak, right? The bits alone are not enough. You have to know what they represent, what encoding has been used in storing them in memory. All right. This is the reality of the world of hardware, right? It's something that higher level languages are trying to hide and abstract, and they do that with varying success, right? So every once in a while, this abstraction leaks. The fact that you're having different same bits with different encodings sort of leaks into the higher level language, and having that awareness is important, right? We're going to move on to pointers next time, where hopefully what you have learned here will help. I am not going to bring this up again. I know I owe you homework, and it will come. It will come. Sorry for the delay. Yeah, so this weekend I'm going to have a little bit more time. I've been quite busy the last week, and I'm hoping to update all the files properly and have all the recordings uploaded, and I'm going to release the first homework as well. Cool. Thanks for coming. See you next time.